Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will continue our learning on CO2 sequestration modeling using CMG software. And in this series of videos, we are going to construct the full case, which will include structural trapping and then solubility trapping and then dissolution trapping, solubility trapping, and then lastly, which we will construct today, is the mineral trapping. So it's going to be very interesting and important, but you need to understand that mineral trapping requires a very long period of time to complete or to occur. But still, it's very important because, yeah, later on, the CO2 will experience mineral trapping as well. So although in maybe our lifetime, mineral trapping will not be completed, but we can be sure that once we inject the CO2, later on, though it takes a very long period of time, CO2 will be trapped by the mineral trapping. So that's why we still need to model the mineral trapping. Okay, so let's go ahead. First, we go to our folder and let's find here case 3B, and we are going to take the WinProp. Okay, WinProp 3B, the dot. This one, WinProp case 3B. In this case, we have already structural hysteresis and solubility trapping. Copy, and then I'm going to erase everything first. Okay, and then paste it here. Let's change it to WinProp case 5. Okay, good. And then mineral. Okay, and then here we go to folder 5, and then let's drag this one and put it on the WinProp. Okay, so we are now inside the WinProp. Let's rename the case. Here, title EOS units, change it to case 5, structural hysteresis solubility, and lastly, mineral trapping. Okay, so far so good. And then as usual, click save. Okay, now let's navigate to the CMG GEM EOS model here. Okay, and then you can see here we have print component properties for GEM, blah, 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 right? Reservoir temperature for GEM fluid model, 50 degrees centigrade. Okay, and then you can also see recalculate solubility parameters at pressure and temperature 50 Celsius, and then pressure 11,800 kilopascal. Now click on this, select GEM reactions and or define polymer or non-reacting aqueous components. Click on that. Very good. Now we have several tabs. We have actually 5 tabs. Now reaction aqueous component, reaction selection, mineral reaction data, aqueous phase model data, ion exchange reactions. Now let's select reaction selection. And we have reaction type selection, aqueous species reaction, and also mineral species reaction. First, we will select here aqueous species reactions, and then we have database available reactions here. Okay, and for our mineral trapping or for our reaction, we are going to select, go down to number 82, CO2 in aqueous phase plus H2O. It will result in H plus and bicarbonate. All right, so let's click on that. Okay, so just click on this and then it will be transferred on this selection or selected reactions. 83 as well. All right. So CO2 it will produce this one plus hydrogen plus it will produce HCO3 minus. And then also reaction number 355 to produce water, H2O. Okay, so far so good. And then for chemical equilibrium equation deviations, I mean derivative, we select numerical instead of analytical. And for mineral precipitation or dissolution rate equation derivative, we also select numerical. Okay, very good. And then here the numerical method is used for calculating chemical equilibrium equation derivatives and mineral precipitation dissolution rate equation derivative. All right, so we prefer performing the derivative calculation using numerical method. And then we move to mineral species reactions. Okay, previously we select aqueous species reactions. So now species reaction or reaction for the mineral species. Okay, and we will find reaction number 31 for our minerals. Anorthite, you can also double click. 112 for calcite. And then lastly for kaolinite, number 292. Okay, pretty good. So we have 3 mineral species reactions here. And then we move to mineral reaction data. All right. Here, mineral reaction data, and we will add reaction parameters in the window. And yeah, I will expand this. Can I? All right. And we also need to check this one, resistance factor calculation. Open the drop-down menu, and we are going to select calculated with Kozenik-Karman formula. And the formula's exponent value by default is 3. All right, this is for the permeability variation due to porosity change because of, mineral precipitation. Okay, so now let's input the data. Mineral reaction, we have 3 reactions. And mineral molecular weight, internal. Mineral mass density, internal and kilogram per meter cube. Now, reactive surface area in meter square per meter cube. We are going to input 88 for anorthite, 88 for calcite, and 17,600 for the, for the kaolinite. Move to the right side. Now for logarithmic rate constant at reference temperature, -12, -8.79588, -13. And then for the activation energy for the reaction, this one, and then for this one, 41,870, 6276260. And then for the reference temperature, we prefer selecting 25 degrees centigrade. And leave others as per default. Okay, and then we move to the next step, Aqueous phase models data. And we select B dot model for the aqueous phase activity model. Hopefully later on we can talk about this B dot model. All right. And then for the almost there, I think. Not this one. We will navigate to the component selection properties node and we will choose aqueous phase. So Okay, so I think we can finish this one first. Click on OK. And now let's find, wait a minute, for the component, this one. I have difficulties in finding this one, component selection properties. And then let's go to, yeah, here we have the component CO2 and methane. Go to Aqueous phase. And we will specify the NaCl concentration. And it's going to be 0.1, but we will change the unit. The unit is molality. Mole of the, you know, this one, mole of the salt, NaCl, per kilogram of the water, H2O. We will maintain the harvest method. And then I think pretty much that's all. Okay. And a little bit short note for the salinity calculation. The user can choose the option for calculation of salinity using Cl minus and Na plus ions concentration, or we can also use a constant salinity. All right. And in this case, we will use constant salinity, of course, with this value 0.1 in terms of molality. But you can also select, or you can prefer select performing the calculation for the salinity by considering the ions of Cl minus and the Na plus, the concentration of the ions. Okay. So far so good. Now we will go back to the CMG GEM EOS model. And from here, again, select GEM reaction, and we will navigate to the aqueous phase model aqueous phase models data. Here we select use constant salinity, 0.1, and we will enter here aqueous phase threshold mole fractions. We can read the description. Mineral precipitation or dissolution rates will be set to 0 if the mole fraction of the gaseous component in the aqueous phase is less than the specified threshold value. Okay, and we will select 0.0001 for the CO2, and for CH4, it really doesn't matter because CH4, remember, in our case, is the trace component. So you can just input 1, that doesn't matter. For the sake of simplicity, we use value of 1 there. Okay. So again, this is the aqueous phase threshold mole fractions. This is important because, you know, the dissolution or precipitation rate will be set to 0 if the mole fraction of the component in the aqueous phase is less than the specified threshold value. So if the gaseous component or the mole fraction of the CO2, again, if the mole fraction of the CO2 is below this value, the precipitation will be considered 0 rate. Okay, because, you know, the reaction rate, precipitation rate, dissolution rate will be determined by the mole fraction, by the concentration of that component. Okay, so that's why the threshold is important, because now we are telling the software, if the mole fraction is very, very, very small, then you can consider the reaction rate for that component will be, you know, will be 0. Okay. And again, CH4 is trace component, so whatever the mole fraction below 1, it will be considered 0 rate. Okay. So we can click OK now and save, and we are done. Okay. We are done in this video, and in the next video, as usual, we will continue with the gem and so on and so forth. Okay. But wait a minute. Yeah, we will not end until we, of course, as usual, click on run. Okay, so the calculation is very quick, very fast. And now we have the result. Okay, here we have the result, and we go to our folder and we will find the .gem of our WinProp. Okay, so now we are back in our folder, and as you can see, when we click on run in the WinProp, we can produce this .gem file. This gem file, contains a very important keyword that we will use in our .dat for the builder to continue our modeling. Okay, but I think regarding the WinProp job, it's almost finished, so we can close this video. All right, so I think that's all. I hope you enjoyed this video. I hope this video is useful. Thank you so much for watching, and see you again in the next episode where we will continue our modeling to finalize the mineral trapping. Okay, see you again. Thank you.